So we're going to dig in a little deeper now into character tables and see how we can use them to take advantage of character tables to solve problems that might not be trivially obvious by simple inspection, as in the case of C2V. And we'll look at this by considering explicitly the example of a C4 symmetry operation for vibrational sum frequency generation, and at the end tie it into what you would get in the case of second harmonic generation. And we'll do it in a fairly formal way, but before we get there, let's first do a simple guess and check approach. And we're going to be considering this E transition, because that's the tricky one. We have these tensor elements, or these matrix elements, the linear and the quadratic terms are in parentheses. And so there's relationships between those that are not obvious based on the character table itself. And what are those relationships, and how do we tease them out based on the toolkit that we have available to us? So let's first look at for C4 symmetry, there's really only two sets of symmetry operations that matter. There's the C2 set and the C4. Now let's look at the C2 first, because it's a little bit easier. For the C2 symmetry operation, you're taking x all the way around into minus x, y all the way around into minus y, and z stays the same. And so this is the set of tensor elements we get. And we're not going to bother applying symmetry operations and doing anything formal right now. We're just going to recognize that if I've got a C2, that if I have this inversion of x, and every time I have a single x, I'm going to get a value of -1 somewhere along the way. And so you can just basically say, for a beta that leaves itself unchanged upon application of the symmetry relationship, which of these, in other words, it transforms as the totally symmetric, which of these is not removed? And if we look at xxx, you can see that I'm going to get a -1, a -1, and a -1 upon performance of the C2 operation. So this one goes away. This one also gives a -1, -1, -1. This one is fine, because I've got -1, -1, 1 based on the C2 symmetry operation. And then I'm just going to quickly go through the list here and cross off all the things that go away from having either having an odd number of xy's in combination. I think that one's gone too. That one's okay. Gone, gone, gone. Yes, and that one goes away, and I think that's the set. And then we look at the C4 operation. What that does is it takes x into y and y into -x. This one won't actually remove anything from our list anymore, but it might simplify a few things along the way and identify some additional relationships between these tensor elements. For example, if we have y going into x, then I know that my xxz tensor element is going to go into my yyz element. I'm going to change pens, actually, just to make it a little clear that we're looking at the next operation. So these two are going to be equal to each other. So now what we have is xx from that C4 operation into yy. Okay, and then if we go x into, let's look at this one next, and we'll have a bunch of these. I'll write them all down. So we'll also have zxx equals zyy, and xzx equals yzy. There. And zzz doesn't do anything. So what about xyz? Here's where things get a little more interesting. X goes into y goes into -x, and z stays the same. So what we have is xyz equals -yxz. And we can continue on with the same line of thinking. yzx equals -xzy, and zxy -zyx. Okay. So that we got just by inspection and intuition in terms of now taking x going into y and y going into -x. Can we come up with a way of doing this more formally, and indeed a way that would allow us to look at symmetry relationships like six-fold rotation, three-fold rotation, relationships that might not be as obvious at the outset as the C4 example, but this way we sort of know what we're going to get in advance, so it makes it a bit easier to look at this. Well, if we know that the symmetry operation leaves the system unchanged, then we end up with something, well, not necessarily unchanged, but we know that if I apply the C4 operation on a transition moment, I'm going to get the value in the character table, and this is the value of lambda here. This actually, if you look at it, is exactly what you would solve in an eigenvector eigenvalue problem. We've got a matrix times a vector yields a scalar times that same vector. So if I know the eigenvectors and eigenvalues of this matrix, I should be able to identify what relationships between mu, in other words the eigenvectors, will yield the corresponding eigenvalue that we want from the character table. Hopefully that makes sense. Come on, computer. So if you take this matrix and plug it in, you recover 3 eigenvalues, I, negative I, and 1. The 1 is going to correspond to, in this case I'm looking at the C4 operation, the 1 is going to correspond to the A. There is no eigenvector or eigenvalue of negative 1. In other words, there's no way a transition moment can recover a value of 1, which is why we have a big old zilch here in the linear term in terms of the B state. But I can get the other 3 just from a vector transformation. So if we look then, take this I, and we're going to focus in on the E transition. If we take the I eigenvalue and ask what are the eigenvectors that correspond to recover that value of I, it's 1, I, and 0. So this means that the vector, the relationship between mu x and mu y to recover this first entry right here is that mu y equals I mu x. Okay, so we have a 90-degree phase shift between mu x and mu y, and they both have a non-zero component when recovering that eigenvalue. Similarly, if you look at the complex conjugate, it just gives us the complex conjugate all the way through for the eigenvector as well. So that now is a way to understand where the I and the negative I come from and why we have to have these in parentheses, because they're tied together through this relationship. Now, how do we then ask? Well, we can ask easily. How do we then solve for the quadratic term as a prelude to the cubic term, which will correspond to the second order nonlinear optics? It's the exact same approach. We're going to have an eigenvalue. Now, let me just go ahead and get this thing out of the way so it's a little bit easier to see. We're going to have an eigenvalue and a matrix. And we want the eigenvalue. Well, if we can get the eigenvalues of this matrix, we can then find the corresponding eigenvectors in alpha. So the eigenvalues, in this case, we get the full set of all 4 of them that we anticipate. We have 1, negative 1, I. Let's go ahead and erase these, and we'll switch to red again. We have, for the C2 or C4 operation, we've got 1, negative 1, I, and negative I, just like you'd expect to have. So you can make the eigenvector out of any combination of these 2 vectors. In other words, any linear combination of these will satisfy the eigenvector-eigenvalue relationship that we require. And if we look at the elements, what do they correspond to? Well, in this case, we have alpha xz and alpha, yz, and then this is alpha zx and alpha zy. And they're tied together. In other words, we can't really look. I can't really look. Here we go. Put that in red. That's alpha. We can't separate the xz and the yz components in this quadratic term, but we can write this as any linear combination of the xz and yz and the zx and zy will recover the corresponding eigenvalue. So this is where this relationship comes in. We still have this 90-degree phase shift between xz and yz and between zx and zy. It manifests both in the transition moment and in the alpha, and that's how we can interpret and identify the relationships hidden in those parentheticals. For completeness, let's go ahead and explore and carry this out also for the A and B transitions. So if we look at the transition moment, or the eigenvalue of 1 for the C4 operation, that'll yield the A transitions. And the eigenvector is 0, 0, 1, which corresponds to the transition moment for the linear. The eigenvectors for alpha that recover about an eigenvalue of 1 are these 2 vectors. You can see we've got alpha xx and alpha yy, and then we have alpha zz. And you can see from this eigenvector why we have this form for the quadratic tensor. It really is xx plus yy is the eigenvector. For the negative 1 eigenvalue corresponding to B, there is no transition moment, as we've already said, but if we put in the negative 1 for alpha here, we can see that we end up with xx minus yy as the eigenvector, and xy minus yx, which is shown and indicated by the xy.